right? Because I've got a gaggle of kids like you do. I've got 10, you've got 9. I'm constantly forgetting their names. If I wanted a chip just to do that, to run that through a fab and do all that would be billions of dollars. So that doesn't make sense
Well,
to produce one. I need to
right.
produce a billion of those, right, to make it
Yeah.
really
I mean,
worthwhile.
it's the economies of scaling up what you build and sell it out in high volume.
Welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. This is Darren Pulsipher, Chief Solution Architect, author, and most importantly, your host. On today's episode, Embracing Microelectronics, with returning guest Dave Richard from Intel. Dave, welcome back to the show.
Thanks, Darren. Well, I'm glad to be back.
It's been a long time, Dave, since we've talked.
Probably earlier
Well, at
this
least
year.
on the show.
Well, we talk all the
talk
time, but on the show, it's
yeah,
probably been a year since I've been on the show, and
yeah,
I'm
maybe. Yeah,
excited to
it's been. I'll have
get
to go
back in
back
the
and
groove.
look. Yeah. So, hey, today we want to talk about microelectronics. But I don't know, since it's been such a long time, let's first talk about Dave Richard. Who is Dave? What is Dave's superpowers? What's his backstory? Every superhero has a backstory. What's Dave's backstory? Give us a little bit of who Dave Richard is.
Oh, I'm a dad with a bunch of kids, and my wife Sarah and I, we enjoy family life, but I enjoy electronics, really have, since I was younger. So my background on the professional side is expertise in acceleration type products, FPGAs, ASICs, and how those fit into systems. So I've enjoyed doing that with Intel. I came from Altera into Intel and had a number of roles, most of them working on architectures with customers in and across the defense industry and what I would call critical infrastructure. Things like industrial, telecom, financial, healthcare, etc. There's a lot of parallels with those groups, with military and the intelligence community. So, enjoying being with Intel, enjoying being another solution architect along with you, Darren, and others on the team.
You know, it's really interesting because a lot of people, when they think of Intel, and rightfully so, they think of CPUs. And when a lot of people, when you mention the word microelectronics, most people go directly to, oh, you just have a CPU. A CPU does everything. But that's not the case. Not at all.
Right. Microelectronics is kind of the umbrella for all these magical devices that go down on these circuit boards that run all of the data processing that we need and handle all of the connections to move data and information across systems. At the very
Well,
bottom of the barrel of where that magic happens, it's a microelectronics device.
okay, so it's not just the CPU. The CPU is like the brains, but microelectronics is everything else around it? Or
Yeah.
does it include their own brains and things like that? I mean,
Yeah, so a
where,
microelectronics device is simply a circuit. In our
oh,
house, we've got circuits that turn the lights on with switches, and quite literally, on a microelectronics device, a special piece of silicon is at the atom level circuits and wires and switches. We call those semiconductor devices, and the switch isn't a switch on our wall. In this case, it's a transistor. And an intelligent designer builds a design to do a certain function. That function we might call a CPU, a general compute processor, or a GPU, a graphics compute processor, or it could be a network interface. All of those are simply circuits that then get printed down on silicon and packaged up into a device with some amazing technology that then goes on a circuit board, and we build systems out of them.
okay, so there isn't just one type of microelectronic. Not everything's a CPU.
That's right.
So there's specialized things that are out there that there's a lot of them, right? There's not just even a dozen different types of microelectronics. There's
There are
hundreds, if not
thousands.
thousands.
The ones we hear about commonly, CPUs, GPUs, etc., those are ones that generally get a class that the class of engineering and consumer folks recognize that here's a class of functions called general processors. We'll call those CPUs. Here's another
Okay.
class of ideas and designs that are meant for processing graphics for gaming or any other type of movie generation. We'll call those graphic processors. So you'll hear about general terms, but really it's just to keep our language on the same place for generally what we're talking about. But all of them, even some of the ones that don't have a classified area, they're all microelectronic designs. The designers create circuits, very complex, with a bunch of software tools and print those in silicon.
Okay, so why don't I just create specific devices for specific things that I need? Because if I do that, then I don't need software. I can just I could just have this chip do exactly one thing. Why don't I just produce a bunch of those instead of having a general CPU that I have to program and all this stuff? What what's the limiting factor there? Because obviously, if we could do it, we would have already, right?
Well, for those who have the ability to actually print those circuits, the costs are expensive. And so really it comes down to costs. And then to try to
Okay.
create circuits that a wide market can use that can give me a return on investment for those. The technology here is very expensive to build the factories and build the technology, the amount of research that goes into creating the manufacturing facilities. And then the software is the same thing. It's simple to wire up a house. I've got a handful of switches and a bunch of wires, but what we're talking about are billions of switches, billions of wires, and you need specialized software tools to help a designer actually build out that complexity. That's expensive stuff. So both in the designing of these ideas, simulating them, making sure that they actually work, and printing them is billions of dollars of investment. And that has to be returned. And so it's very difficult to just let everybody do that. And it doesn't meet the cost and the complexity to do it by
So
yourself every time.
if I wanted to build a micro device, microcircuit, whatever, that specifically just did a visual recognition of my kids, so I could keep them
Mm-hmm.
straight, right? Because I've got a gaggle of kids like you do. I've got 10, you've got 9. I'm constantly forgetting their names. If I wanted a chip just to do that, to run that through a fab and do all that would be billions of dollars. So that doesn't make sense
Well,
to produce one. I need to
right.
produce a billion of those, right, to make it
Yeah.
really
I mean,
worthwhile.
it's the economies of scaling up what you build and sell it out in high volume. Today's state of the art, you're talking hundreds of millions of dollars to do one state of the art advanced microelectronics device. If you use some of the
Wow.
older, more mature nodes, more mature processing, you can get typically into the millions of dollars. That's just for
So
one shot.
just for one shot, but I can produce hundreds of thousands or millions of those chips. The more I
Yep,
produce, the lower my cost.
that's right. And that's what they'll do. So if you're dealing with state of the art, things like our cell phone, advanced communications, the gaming platforms, the laptops that always have to be faster and lower power, they're going after markets with tens and hundreds of millions of consumers, and hence they have the volumes to support the investment from the manufacturing companies that can support building a $15 billion facility. One factory today, state of the art, about $15 billion just to build that factory.
Wow.
And there's only 3 companies in the world that really are effective at doing that anymore. It used to be lots, but as the costs have gone up, it's consolidated. So you have TSMC, Taiwan Semiconductor, you have Intel, and you have Samsung in Korea. Those 3 companies are the only companies that build state-of-the-art manufacturing.
Latest nodes, always pushing the edge. But there are other fabricators that are doing older nodes.
Hmm.
So if I want to create something, maybe it doesn't have to be super small, um, or ultra small, whatever, right?
Yep.
But I can do that, right? I can say I can go to them and say, hey, I only need 1,000 of these things. They're more than willing to do something like that because their costs are already They've already sunk
Yeah.
all their research costs. They've already done all that.
Yeah, there's a lot of finance expertise that goes into building these factories, getting them financed, and then amortizing the costs down so that then they become older technologies. They still keep them running, and then they have a lower cost model. Of course, you're not getting the latest and best technology. So, for instance, if I was building cell phones to compete with iPhones or Samsung, if I don't have the latest technology on the most state-of-the-art um, fabrication environments, I won't compete because my silicon will be slower, more expensive, more power hungry than the newest. However, if I'm in a car, lots of volume there. I don't need always the absolute state of the art. I could use something that's a little older and still get lower costs, very cost sensitive market there. Same thing with industrial, same thing with healthcare, and some other industries fall into that area where they don't need state of the art right away. They can still get the benefits of an advanced node that's not right at the leading edge, more mature, less risk, and take advantage of the costs there. So it depends on what industry you're in.
That's it. So it's really fascinating to me because anytime I think about microelectronics, I don't think about the cost as part of one of the key factors, but it absolutely is because I just think, oh, I want on the latest processor node because the technology is the latest and greatest. That's not always the best answer, is what I'm
It's
hearing.
not. And in the consumer space, most times people think of microelectronics, they think of laptops, they think of their iPads and all the other competitor pads. They think of their cell phones, the things I mentioned in the gaming platforms. They don't want it unless it's the fastest and lowest power, and they're willing to pay for it. But when you think about buying your appliances for
A
refrigerator
refrigerator.
and
Yeah.
your new clock, right? All of that kind of the stuff that you don't even really think about microelectronics. Those are more mature, cheaper products taking advantage of older manufacturing processes. So,
That's really fascinating. So we talked a lot about consumer. What are
mhm,
some of the challenges for government in
sure.
microelectronics? Because government's a different space than consumer.
Yep. So, government, let's break government into the defense and intelligence, and then government
Okay.
as more of the civilian side. In the civilian side, the federal civilian government, they're consuming typically commercial products, usually. It's where you get
Okay.
into the defense and intelligence where they need some special things. Much of what they address is like the commercial market. We have cars and vehicles commercially. They also have cars and vehicles and tanks and such that can take advantage of more mature technologies as well. But in the commercial world, we've got communication devices. And in the government and the military, they also have communication devices where they need the latest and greatest, the very best devices. So those devices, just like commercial, a subset of them need the world's best state-of-the-art manufacturing capabilities. The difference is this. If I buy my cell phone, generally, I don't have a problem if the cell phone was designed in another country. But in the government, military, and intelligence, they have certain ability to operate if it wasn't designed in a favorable or friendly nation to that nation. So there are two areas that the government looks at. One is what I would call the workload. That is, I need a CPU or I need a GPU. And just like commercial would, and gamers would need a GPU for doing graphics, so does the intelligence and the military. They need to process graphics as well for simulators and various types of training, as well as out in the field on cameras and such that they're monitoring
Right.
activity. But what they have is more restrictive abilities to operate. I call those ability to operate capabilities. These are things like I can't use that device unless it's secure. I can't use that device unless its temperature range, the environmental abilities of it can stand extreme heat. If I put my cell phone out in under the sun, I'll get a heat warning and it won't work. But I can't have that
Oh, that
happen in the military and they're out in the desert. Same thing with
right. That
cold.
makes sense.
So
So
these
so their
abilities to
operating environment.
operate for microelectronics, these are another layer of complexity to microelectronics that the government typically has to deal with. And so that impacts manufacturing. It also impacts who designs what, where they design it, how they handle that data.
Okay, so it's far more complex than on the commercial side because of the restrictions and also, like you said, the operating environment, space,
Yep.
heat, cold, all those other things. Does it need to withstand an EMP? I don't know.
Yes, those are all valid
Some
concerns
of
for
those are.
military. Now, one other challenge, Darren, is the military. When you look at the economics of it, um, Samsung, Apple, the folks who build cell phones, they're selling hundreds of millions of cell phones. And their market literally is billions of people. Um, Cars,
You're
hundreds
not
of
doing the
millions
same
of
in the
cars.
military, right?
Military, you can take the entire volume of all the microelectronics of military. It's still small compared to any one of those major markets. So now, when I'm trying to get access to state-of-the-art manufacturing on fabs and whatnot,
It's impossible.
um,
Yeah.
it's hard for the military and the intelligence community to get a seat at the table. One, they don't have the volume that, say, a cell phone or a laptop company or a desktop or big data center company like the cloud service providers have. They don't have the volumes there. Secondly, they're more complex. They have more complex requirements around security and other things related to the manufacturing facilities. So what ends up happening is a company like Intel, like TSMC and Samsung, invest $15 billion in a foundry, a manufacturing facility. They need to quickly get a return on investment from that. So the commercial companies that drive the biggest volume, they get a priority seat at the table. And all the other markets, including military, they get a
They
secondary
fill in
seat.
the empty gaps. Yeah.
And they won't get access to the engineering and the manufacturing that those biggest customers will get until they're done with them, and it's several years later. Um, the other part of that, which is important, is that because of this, our defense industry is used to dealing with more mature nodes, where the design tools and all of the
Interesting.
abilities and
They've
support
been
is
around
much more
for
mature.
a decade. Yeah.
Yeah,
Yeah.
it's
Yeah.
more
Yeah. That
mature.
makes
It's
sense.
easier to use because it's been worked out and flushed out. On the leading state of the art foundries, it's kind of messy there. This is brand new technology. It's very hard to do, and the companies that were willing to risk working in that environment, get to market fast with their best cell phone, better than the others, they're going to get capture on the market. So there's a lot of risk taking up front there on the state of the art manufacturing,
So,
and the
so
government isn't used to
really
that.
this is really fascinating. What that tells me is military and government in general is going to be behind regardless because they're not willing to take the risk on devices, right? Because if I have a microelectronics in a bomb, I want to make sure it does what it's supposed to do and doesn't go off at the wrong time. People
Hmm.
die, right? Or if I'm in manufacturing in government, same thing. Or if I've got a sensor. So what that tells me is they will always be behind as far as the process node technology,
So that has
and
been
that
the
should
case
be okay,
in the early
right?
part of the industry. Go back 30 years. The
Okay,
government used to have a bigger volume. We didn't have cell phones. We didn't have this wide proliferation of
oh, that's
microelectronics and
true.
telecommunications networks. So the markets that exist today for the high volume didn't exist back then. The government actually was a big player, and so they were always a part of the leading state of the art. What's happened in the last 25, 30 years is those markets emerged and they took dominance. So where we are today is true what you say. Most of the government military intelligence is on mature nodes. They're not getting state of the art in the classic commercial microelectronics. What's changing that is things like the U.S. CHIPS Act. The CHIPS Act was money to help collaborate to accelerate onshore manufacturing with companies like ours, Intel, but it also had in it pick the leading defense partners who build some of the world's best sensing technologies and analytic technologies, give them a seat at the state of the art nodes in exchange for some money that helps accelerate the commercial adoption onshore. We have two problems in the US that they're trying to solve, and that is get more state of the art inside of the borders of the U.S., and secondly, get some of the defense folks back up at the seat of the table on state-of-the-art technologies. And those are being worked on as we speak.
So that's the CHIP Fab and ME Commons, the Microelectronics Commons
Yep.
programs
There's a number of
that are
programs in
all
there.
geared towards that. All right, that makes a lot of sense because maybe the military's volume hasn't really gone down at all. It's just it's being overrun
That's right.
by all the new markets that have created that are requiring microelectronics. Is that just going to get worse?
In fact, it's
Because
increasing. The military volume on microelectronics has been increasing, just doesn't increase at the rate that the commercial. So we're always going to
do you
have this
think?
challenge.
But do you think that's going to change with more autonomous fighting machines like drones and maybe robots and things like that? Because they need a lot of microelectronics. So do you think if they start producing those in volume, that will that ever be enough volume
I
to
don't
put them in?
I don't foresee that ever is enough volume to get it in front of the world's biggest consumers of microelectronics. However,
I hope
the
not.
fact
Right.
the fact that it does increase means that each individual opportunity there, if government uses its influence, can become a valuable opportunity for these commercial fabs and continue to push them up into the priority list for state-of-the-art access. The second thing that government does, besides grow the volume of microelectronics, is actually help to accelerate companies in the commercial space to build these state-of-the-art fabs. So that's money that helps bring commercial onshore manufacturing, help offset the costs for companies onshore in U.S. or other nations relative to doing those in other regions of the world. And in the process of doing that, adding money to enhance those fabs and factories so that they can support some of the special requirements that are complex for security, special environment, managing the data, making sure that designs are even more secure when they go through manufacturing. So government can
It's
help
not.
with subsidies as well as volume increase.
So the special requirements the government has when it comes to fabs producing really don't have to do with the process node itself. It has to do with securing the facility, making sure the right people are seeing the right things. It all has to do with security, not necessarily changing the process nodes themselves or how they're printed, the circuit boards are printed. It's
There are some
all about.
proposals. Yeah, there's some proposals that would have them change it, but there's many options for handling some of the unique requirements. Some of that can be done purely on the design and then just printed
Okay.
into the silicon the way that you design it. And there are some that have to be done for security in the
The manufacturers.
manufacturing facilities. So it is a mix. But
Okay, so wait, we got to back up a second
oh
because
yeah,
we danced around an issue here, which is I don't fully understand the whole microelectronic stack because you've been saying parts of it,
hmm
but can you explain? Because if I look at the fab as just a printer, it's just printing, right? That's all the fab is really doing. It's doing a lot more than that. I mean, it's
yeah.
$15 billion to make one. I don't know anyone that makes a $15 billion printer, but I guess TSMC and Intel do because they're just printing circuit boards. That's all they're doing, or they're printing circuits,
Yep.
right?
So why don't we'll call
So
it the
what goes on
microelectronic
before all
stack.
that? Yeah.
Yep. Let's call it the microelectronic stack. Most consumers, the average person goes out and buys a laptop. That's already integrated technology to build the laptop. They turn it on and they start typing away and work it with the
Right.
mouse. And if they want in their house, they'll network them all together. Everybody in the house has it. My kids all have different devices. We're all networked with a router. So we have different devices like that we bought and they're networked. Call that a system when they all work together. But and I can tie that further to a system in the city where I'm talking out through my internet to talk to different systems. That builds the systems out wider across the globe. But go the other direction. go inside the laptop. Inside the laptop are a bunch of circuit boards, and on those circuit boards are microelectronic devices. So I need a set of microelectronic devices to build a circuit board. And then if I go inside the microelectronic device, I can break that down into a couple pieces. So first, to build that microelectronic device, I need an idea. Engineering teams have an idea of what circuit they want to build, and they want to apply it to either a processor or graphics. We talked about these before, or some radio, what have you, memory devices, etc. Those ideas have to be implemented in what they use are software tools to put that idea into a description that they can print it on a piece of silicon. That turns it into a real circuit on a piece of silicon. That silicon then gets, each idea is now an independent piece of silicon. I can print many different types of circuits. And then what I would do is put those pieces of silicon together, and I would actually, what they call packaging, I would package them up. One way to think of this, Darren, is I have an idea and I'm going to present onto a PowerPoint. So I use PowerPoint on my computer to capture my idea. Then what I need to do is go to a place to present it. I'm going to print it out. I'm going to print it in paper. I can print it on a black and white printer, or I can print it on a color printer, or the latest thermal glossy printer. Each is a different printer. That would be different pieces of silicon. And then when I'm done printing out, I've got 3 presentations. I print all 3, and then I want to put them together in a binder. I can pick from a 3-ring binder, a spiral round binder, different things to package them together. And in the microelectronics world, my idea is a circuit that gets printed onto silicon, different pieces of silicon, and then they package that up into a device with multiple pieces of silicon, and then that goes to a company that puts it on an electronic board into my laptop, and my laptop then I get to use.
Okay, how often is it that an organization that comes up with their idea, and we call that intellectual property, right? IP.
Yep.
Silicon IP, right? They come up with the
Yep.
idea, they put it into this special language that all the fabs use, right, to print, right? It's a special language that they use. Let's just put it that way.
Yeah, let's
right,
not go
that
into
they
that.
use to
But
describe it.
ultimately, they're printing it on a piece of silicon with some very expensive. This is what the $15 billion factory pays for. We're talking about printing at the size, nearly the size of atoms. It's amazing, and there's a lot of things people can go look at. But it's crazy technology and very expensive.
How often does a company produce an idea that gets put on silicon and that's it? That piece of silicon runs everything by itself. That never happens today, right? I guess Intel with their x86 processor, right? I mean,
Yep.
It's a general processor. I can just buy that piece of silicon and it works.
Yep. So normally it's a cycle of in rare cases, 2 years, but normally it's 3 years or more. And you'll have different generations. And, if I build my PowerPoint presentation, I print it all out and package it up and hand it out to people, and then I go, I want to improve that. I got to go do it all over again. So companies on the commercial,
off of what I already did. I would hope.
Yes, so they'll build off of what they already did. Exactly.
Yeah.
And so they're using design from the past, their IP. I think where I would take this is that different companies see these big markets, and the x86 architecture is a form of a CPU. There's ARM architectures. These are all just different ideas, different ways to design circuits. Now, they compete with one another. And NVIDIA and Intel compete, AMD competes with Intel, ARM competes, and different companies that use ARM, they all compete with one another. So on one level, when they build a final device, which has all their printed ideas on silicon, packaged up, and they sell them to companies that put them on circuit boards, they'll call that a commercial off-the-shelf COTS product. And Intel will build a COTS x86 processor, and AMD will build a COTS x86 processor, and we're competing those processors. What we can do though is we go inside and say, hey, AMD built pieces of silicon inside of their processor, and Intel built pieces of silicon, and NVIDIA built pieces of silicon. Maybe I can take some of NVIDIA's pieces of silicon and some of Intel's and some of others and put them together and build a new device, package some of NVIDIA and some of Intel together.
Oh, interesting.
And I'll create a new device that way. So in one sense, when I built COTS products and ship them out commercially, I'm competing. But with the second idea, which is I can use a piece of NVIDIA and a piece of Intel, put them together to build a new device, now Intel and NVIDIA might be partners. And then they build a separate device together and sell that. So this world of competition in microelectronics, those who design the circuits and those who manufacture them, we have the ability for sometimes they're competitors and sometimes they're actually partners.
So the lines get very fuzzy then, or foggy on your competitor or your partner, right? It could be either way depending on the market.
Yep, and in government in particular, they like a little bit from company A and company B and company C.
Well, because they don't want dependency on one company.
Yeah, for particular missions, they would love to get state-of-the-art specialized things to give the defense and intelligence community a better way to defend the country by mixing them together. And because Intel has both designs and IP and ideas, and we print those, and we also have manufacturing facilities, we can actually help be a critical player out there where we can pull some of those other companies that have great capability that might traditionally compete with us on, say, a laptop, but when it comes to specialized designs and specialized products, they'll be a partner of ours.
That's very cool, and that's through our packaging technology that allows that to happen, right? Because not all packaging is the same. You know what this reminds me of? It reminds me of PowerPoint presentations that we use all the time. I create one, you create one, you take some of mine, I take some of yours, we smash them together, create a new PowerPoint that's targeted for a specific customer. Do you see more of this co-opetition happening? Has the packaging technology made this so this is now easy to do? Or are there still some technical barriers that need to jump?
So, I'm hopeful that we're going to continue to evolve to create more partnering and more collaboration. But there are some technical and some economic barriers. Some of the technical ones are, if Darren, you produced a piece of silicon and I produced a piece of silicon for our own individual COTS products.
Right.
Where pieces of silicon talk to each other on a circuit level, well, they have to meet and match. They have to talk the same language. It's like when I have my laptop and my Wi-Fi is down and all I got is Bluetooth. Well, Bluetooth can't talk to my Wi-Fi router.
No,
I have to have Wi-Fi talking. And so the industry is just starting to build some standards where the standard says one of those is called Universal Chiplet Interconnect Express, UCIe. And it's a standard that's an open standard that says if you build this interface from one device, I can build it as well, and our chips would work together. So we're still pretty new in that area. It's going to take some time to make that work so that we can all mix and match our parts.
Well, it sounds like if we can get engineers to drive to that standard, things will work well. If we let the finance guys do it, they'll be more protective of right? Of their, I don't want to share. I don't want. So we'll see who wins that battle over the next 10 years.
And this is an area I hope that the government can help facilitate this. The government has a role in helping to promote standards. And they can do that by helping get into state-of-the-art, working with companies like ours and others on some of our latest and best designs, and helping us along the way to accelerate these types of standards.
This has been fascinating, Dave. I mean, every time I talk to you, I learn something new. Thank you for describing this, because this is very a black art for a lot of people. They don't know. They just think, it just magically happens, right? So thanks for coming on the show
You're
today.
welcome. Yep. We'll be talking more about this in the future as well. Thanks a lot, Darren. Appreciate it.
Thank you for listening to Embracing Digital Transformation today. If you enjoyed our podcast, give it 5 stars on your favorite podcasting site or YouTube channel. You can find out more information about Embracing Digital Transformation at embracingdigital.org. Until next time, go out and embrace the digital revolution.